Applications of forces, rigid bodies. So we're looking at static systems, so no bodies are moving, and a rigid body would be something like a rod or a ladder leaning against a wall. So for a system to be in equilibrium, the resultant force in any direction would be zero, the resultant moment about any point would be zero, and if a system is in limiting equilibrium, so friction applies, so we're looking at rough surfaces in contact with each other, then the maximum frictional force would be F equals mu r, where mu is the coefficient of friction, and we know that friction varies between 0 newtons up to a maximum given by this formula. So here we have a rod which is in contact with a smooth peg, and the rod is also resting on a smooth horizontal surface. As all surfaces are smooth, the rod will move until it falls off the peg and falls onto the ground. There are no frictional forces. Now if the ground was slightly rough, so the coefficient of friction is small, but the peg is still smooth, but we do have some friction here now, then the rod will still move in this direction, but now we have a frictional force opposing motion, but the rod will continue to move until it falls off the peg once more. And now this situation where the rod is in limiting equilibrium, it is about to slip. The ground this time is quite rough, and there's quite a lot of frictional force in this direction, and again the rod would like to move in this direction, and the frictional force is opposing that motion, hence the direction of the arrow. And for limiting equilibrium, where the rod is about to slip, the frictional force is given by this formula, F equals mu r. This is the example that we're going to look at next. So the rod weighs 40 g newtons. It's at an angle of 15 degrees to this rough horizontal plane. So we have a normal reaction here. That's the normal reaction force between the ground and the rod. The ground is pushing back on the rod, so the normal reaction force needs to be perpendicular to our horizontal surface. The frictional force, the normal reaction at the peg, and this distance is 5 meters, 3 meters and 2 meters. Because of limiting equilibrium, F equals mu r, this is the frictional force here, and the resultant force in any direction, so if we resolve forces parallel or perpendicular to the incline or to the horizontal surface that the rod is resting on, the resultant force in any direction will be 0, and the resultant moment taken about any point, so about this point or this point or this point, will be 0. So let's start by taking moments, and I'm going to take moments about point A, and I've chosen that point because any force that passes through this point, the distance between the force and the point will be 0, so that particular force will not be a part of our calculation for moments. So to find P, the normal reaction here at the peg, so taking moments about point A, and the moment is the magnitude of the force times the perpendicular distance. So for the weight, 40 g newtons, so we have our force, the perpendicular distance is along here, and in this right angle triangle it's just 5 cos 15, that distance there, 5 cos 15, and it's perpendicular to the force, and this force is going in a clockwise sense around point A, so it's a positive moment. There we go, 40 g times 5 cos 15. Now we look at force P, and the perpendicular distance to that force now is just 8 meters, so it's 8 times P, but again around point A, this force is going in an anti-clockwise sense around point A, so it's negative, it's the opposite to this direction. And then we solve to get P. And now to work out F and R, well, F and R are perpendicular to each other, so if I use these two directions to resolve forces, so I need to look at force P, and force P has a vertical component and it has a horizontal component. Its vertical component, based on this angle here, this is 15 degrees, the same as this, so P cos 15, and the horizontal component here will be P sine 15. So resolving forces horizontally, we have this force in this direction and this force here in this direction. These are the only two horizontal forces or components of horizontal forces. And vertically we have this one, so pointing up, this one is pointing up, and this one is pointing down. That's all of the forces considered now in our two perpendicular directions. So let's have a look at this direction horizontally. So we have force F, and it's positive because it's in this direction. Then we've got P sine 15, but that's pointing to the left in the opposite direction to this, so it's negative. And we know the resultant force is 0. We're looking at a static system. And we've already calculated force P, which was 236.65 newtons. That's the reason for using extra significant figures here, so that we don't lose any accuracy for subsequent calculations, like here. So F is 61.25 newtons. And then finally we look at the vertical direction, so resolving in this direction, the upwards direction is positive, so we've got R plus P cos 15 minus 40G equals 0. Resultant force is 0, and again in this we know what P is equal to already, and R would then be 163.41 newtons. So to work out the coefficient of friction, mu, so we have the frictional force, we have the normal reaction, we have a formula that links them, we substitute the values in, and we rearrange to get the coefficient of friction, 0.37 to two significant figures. For further practice, try these questions.